everybody. Hope the first 3 sessions have gone well. You are now at the halfway point, so this is session number 4. Session number 4 is going to run us about 46 minutes long. I'm not sure if you'll have access to the quiz that's on Canvas, but just in case, I left a debrief in there about some of the commonly missed questions. I'm not 100% sure right now if you will have access to that, but if you don't have access to the quiz, please feel free to skip over that part. It'll also be a continuation of some stuff from physics, so we'll talk about the electromagnetic spectrum, wavelength, frequency, and kind of how to handle some calculations there. Remember, you are not expected to memorize formulas for this Praxis. There will be a small reference sheet for you. But even if you're not expected to memorize formulas, it's still a good idea to know them. Also, you don't have a calculator. So when it comes to some of the math problems, don't get so focused on like, okay, can I solve the math part? It's more conceptual. So do I understand what this question is asking me? So do I understand the concept of how to calculate this thing? Hopefully that makes sense. And hopefully these sessions are helping you. You have 4 more to go. So good luck. Enjoy session number 4 and happy studying. Velocity yesterday. So let's see what we remember. I see brains just a moving and people just a thinking. Good job. Got a couple of answers starting to pop up. I'm gonna give about 30 more seconds before we talk this one through. So let's take a look. I'm seeing a lot of D's in the chat. So let's see if what we're thinking is correct. This problem is asking us for velocity, right? From yesterday, does anybody remember what the formula for velocity is?
Displacement over time.
Good. Velocity is displacement over time. If we put it in our formula triangle, velocity is here, displacement is up there, and time is on the bottom, right?
Mm-hmm.
Now, in order to get this problem, you have to remember that that D is displacement and not distance. So for those of you guys that were telling me D, you were actually calculating speed, which is distance over time. To understand this one, if you look at the displacement here is not 35. And here's why. So if the student walks 15 meters east, say that was 15 meters, and then they turn and walk 20 meters north, right? Their displacement is going to be this missing part because that's how far they are from where they started. So if this were a triangle, a right triangle, you would have to use Pythagorean theorem to figure out this missing side and calculate displacement. So if you do it that way, Pythagorean theorem is a squared plus b squared is equal to c squared, right? So that means you would have 15 squared, which is 225, I think. Let's make sure. Let me grab my calculator, but I'm pretty sure. Yeah, 15 squared is 225, and then 20 squared is 400, right? So that means 225 plus 400 is equal to 625. And then to find our missing side, since this is a squared and b squared, 625 would be c squared. So to find what c is, you take the square root of 625, and our missing side is actually 25 meters. So the displacement in this one is actually 25 meters, not 35 meters. And if you recalculate it, that means the displacement is 25 meters divided by, oh, my bar is in the way there, our 10 seconds for time. So the answer for this problem is actually
C.
C. And I wanted to bring this one up because there was a couple people who stayed on the call a little bit after yesterday, and we did an example that required Pythagorean theorem to get the displacement. So I wanted to give everybody one of these in case they were not on for that piece. When you have a velocity problem, it's kind of a good idea, whether it's distance, displacement, speed, velocity, to draw out idea to help draw out that diagram when you first do it. So just in case you end up with a triangle, you easily see what the direction was and you can figure out, okay, I gotta find the missing side. Because I saw when I started to draw it out, I saw a couple people be like, oh, I got it, the side is missing. So drawing out your distance helps a long way with speed, velocity, all those types of problems. Questions on this one? Sure. So Sam, the distance is your total journey, right? So in this one, if it asked you about the speed, you would just need to add the two numbers together. That's when you would have 35. So the total distance is 20 plus 15. Displacement is just how far away you are from where you started. So if I began my journey at the pink dot and ended my journey here, I'm 25 meters away from where I started. But I took 35 meters for my total trip, so that was my distance. Displacement is the 25. We also said yesterday, so I'm gonna clear some of the stuff off the way. If I walked in a square like this, so if I had 2 meters, 4 meters, 2 meters, and 4 meters, my total distance would be 4, 8, 10, 12 meters, because that would be the total journey I walked. But if I started here, took that whole journey and ended here, my displacement would be 0, because I started and stopped in the same place. Make sense? Cool. So we're gonna talk a little bit more about some physics topics today. I'm again gonna be focused on speed, amplitude, wavelength, and frequency. And to kind of help us synthesize some of the concepts we're gonna talk about today, I'm gonna show us a small video. Sorry, y'all, me and his dad work opposite hours, so like this is the time we switch. So this always gets a little bit difficult. So I'm gonna play this video. It's a couple minutes long, but it's gonna help us give something that we can refer back to when we talk about light and optics and wavelength and electromagnetism. I love TED Ed videos, and even though they can seem corny, our kids kind of like these too. So this is a good one if you need to teach this to your kids later on. If you can't hear it when I hit play, please just let me know. So I think it's set up. Can you guys hear it?
What if you could only see one color? Imagine, for instance, that you could only see things that were red, and that everything else was completely invisible to you. As it turns out, that's how you live your life all the time, because your eyes can only see a minuscule part of the full spectrum of light. Different kinds of light are all around you every day, but are invisible to the human eye. From the radio waves that carry your favorite songs, to the X-rays doctors use to see inside of you, to the microwaves that heat up your food. In order to understand how these can all be light, we'll need to know a thing or two about what light is. Light is electromagnetic radiation that acts like both a wave and a particle. Light waves are kind of like waves on the ocean. There are big waves and small waves, waves that crash on the shore one right after the other, and waves that only roll in every so often. The size of a wave is called its wavelength. and how often it comes by is called its frequency. Imagine being a boat in that ocean, bobbing up and down as the waves go by. If the waves that day have long wavelengths, they'll make you bob only so often, or at a low frequency. If the waves instead have short wavelengths, they'll be close together and you'll bob up and down much more often, at a high frequency. Different kinds of light are all waves. They just have different wavelengths and frequencies. If you know the wavelength or frequency of a wave of light, you can also figure out its energy. Long wavelengths have low energies, while short wavelengths have high energies. It's easy to remember if you think about being in that boat. If you were out sailing on a day with short, choppy waves, you'd probably be pretty high energy yourself, running around to keep things from falling over. But on a long wavelength sea, you'd be rolling along, relaxed, low energy. The energy of light tells us how it will interact with matter, for example, the cells of our eyes. When we see, it's because the energy of light stimulates a receptor in our eye called the retina. Our retina are only sensitive to light with a very small range in energy, and so we call that range of light visible light. Inside our retina are special receptors called rods and cones. The rods measure brightness, so we know how much light there is. The cones are in charge of what color of light we see, because different cones are sensitive to different energies of light. Some cones are more excited by light that is long wavelength and low energy, and other cones are more excited by short wavelength, high energy light. When light hits our eye, the relative amount of energy each cone measures signals our brain to perceive colors. The rainbow we perceive is actually visible light in order of its energy. At one side of the rainbow is low energy light, we see as red, and at the other side is high energy light, we see as blue. If light shines on us that has an energy our retina can't measure, we won't be able to see it. Light that is too short wavelength or high energy gets absorbed by the eye's surface before it can even get to the retina, and light that is too long wavelength doesn't have enough energy to stimulate our retina at all. The only thing that makes one kind of light different from another is its wavelength. Radio waves have long wavelengths, while X-rays have short wavelengths, and visible light, the kind you can actually see, is somewhere in between. Even though our eyes can't detect light outside of the visible range, we can build special detectors that are stimulated by these other wavelengths of light, kind of like digital eyes. With these devices, we can measure the light that is there, even though we can't see it ourselves. So take a step back and think about all of this for a moment. Even though they seem different, the warmth you feel from a crackling fire is the same as the sun shining on you on a beautiful day. The same as ultraviolet light you put on sunscreen to protect yourself from. The same thing as your TV, your radio, and your microwave. Now those examples are all things here on Earth, things you experience in your everyday life. But here's something even more amazing. Our universe gives off the full spectrum of light too. When you think of the night sky, you probably think of being able to see the stars shining with your own eyes. But that's just visible light, which you now know is only a tiny part of the full spectrum. If we had to draw the universe and could only use visible light, it'd be like having only one crayon. Pretty sad. To see the universe in its full spectrum, we need to have the right eyes. And that means using special telescopes that can help us see beyond visible light. You've probably heard of the Hubble Space Telescope and seen its beautiful pictures taken in visible and ultraviolet light. But you might not know that there are almost 20 space telescopes in orbit, missions that can each see part of the full spectrum of light. With telescopes acting as our virtual eyes, both in space and here on Earth, we can see some amazing things. And the coolest thing of all? No matter the wavelength or energy, the light that we see out in the distant universe is the same thing as the light that we can experience and study here on Earth. So since we know the physics of how X-ray, ultraviolet light, or microwaves work here, we can study the light of a distant star or galaxy and know what kinds of things are happening there too. So as you go about your daily life, think beyond what your eyes can and can't see. Knowing just a little bit about the natural world can help you perceive the full spectrum around you all the time.
So we're going to talk about a bunch of the concepts that they mentioned, but I just wanted to show us this to kind of help us give us a starting point. While I fix my screen here, as a fun fact, does anybody know who can see colors better, men or women?
Women?
women. Does anybody know why based on that video?
Aren't they more likely to have like color blindness?
Men are, because women have more cones. So women have more cones, which is why we can see a different range of color than men can. But men have more rods, so they can see better. They can see shades better. So if you ever have like a male friend who likes the darkness and you're like, why it's so dark in here? They see better in dark and like shades than we can. Just as a good job, Sam and James. Y'all can see in the dark. So a couple things I want us to pull from the video. First, light is more than just what we can see. So one of the questions they like to ask you is about this thing called light and how light is energy. So light is a wave that acts like light is a wave. So it's got a mass that acts like a particle and like a wave. So we're going to be focusing on the wave part of everything today. Just so we make sure, wave is something that does not carry matter with it. So a wave is something that actually passes through matter. So light is a wave because it passes through matter. It does not take matter along for the ride. So it's not going to sweep you over like this ocean wave does to the girl. She, in the video, mentioned our good friend, the electromagnetic spectrum. So there's a lot of information contained right in this spectrum. First, this is showing us from shortest to longest wavelength, and it's also showing us from highest energy to lowest energy. So radio waves that come from the radio in your car are the longest wavelength that we have in terms of light, and it has the lowest frequency. Right here, this little spectrum with the rainbow is the very teeny tiny portion of this whole electromagnetic spectrum that we can see. In the video, she mentioned that the visible light spectrum is organized in order from shortest to longest wavelength. So if you think back to good old Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, that's the order in which the wavelengths go. Red is the longest, sorry. Yes, red is longer, blue is shorter. Okay. In the visible link, it is easier for us to see blue, which is also one of the reasons why we perceive the sky to be blue. It's easier for our eyes to pick up that color, so that's why we partially one of the reasons why we perceive the sky as blue. Now, when we think about wavelength and we think about frequency and energy, it's also kind of good to know that the higher the frequency, the more harmful to human health. So when we talked about, if for anybody who missed the chemistry section, we'll come back to it. But in the second one, we talked about alpha, beta, and gamma decay. Gamma decay is an electromagnetic wave. So it's the byproduct of any type of nuclear reaction, and it is just a high energy wave. This is what harms people in terms of nuclear bombs and nuclear reactions. It's the gamma rays. They have a super short wavelength and a super high frequency, which makes them penetrate cells at a very high rate and destroys the cell matter. So that's why they're dangerous. This is also what comes out of the x-ray machine when you go get your teeth scanned, which is why you wear that big old lead vest so it doesn't tear you apart too much. Now, one of the things that we really need to focus on is this thing about wavelength and frequency. So towards the end of the session, we'll do some practice problems with how to calculate these, but I wanted to get us to start thinking about it first. So energies with low waves, a low energy, have longer frequencies. So the shorter your frequency, the higher your energy is. There's a question I'm going to ask you next, and it's going to seem weird, but it's about a wave phenomenon that we probably experience fairly regularly, and it's something like they like to ask us about in this weird format. So the question looks like this. The frequency of 2000 hertz is measured as an ambulance siren received from a detector. What frequency will be detected when the ambulance is at rest relative to the detector? So this seems like a question that you may need to calculate, but how you want to think about this is, so say you are the detector, right? What happens to the frequency of an ambulance siren as you hear it, then it goes past you? Hey, no tea, Amir. It showed y'all the answer a little bit if you saw it.
It goes
But
slow.
anybody have a guess as to what this answer will be?
As it's going away. Maybe let.
I think C.
The answer is C.
The closer it gets, the louder it is.
And so also think about its pitch, right? So as you hear a siren pretty far away, you're going to hear it at its highest range of its pitch. Then it's going to pass you, and then it sounds like a lower frequency as soon as it gets away from you. So it'll be like, woo, 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 as you go past. So you're literally hearing long frequency, short frequency, long frequency again, as it gets right past you. So this question is saying the frequency of a siren is 2000 hertz. When the ambulance is right in front of you, the wavelength is going to be short. So you're going to hear it at C greater than 2000 hertz. Makes sense?
Yeah.
And so this phenomenon, when you hear the siren go past you, is something called the Doppler effect. They love, love, love to ask strange questions about the Doppler effect. And it's always phrased in a way that makes it kind of hard to pick up what they're talking about. But here, the Doppler effect, again, so right when you get close, the wavelength gets very short to you, so the frequency gets high. So wavelength high, frequency is short. So remember that she, in the video, talked about like waves on the ocean. So if you were in a boat and the waves were very, very choppy, they would have a short wavelength and a lot of energy. So you'd be bouncing around going crazy. But if you were on a long wavelength sea, you'd be kind of chilling. That's the same thing with the Doppler effect. The shorter, the higher, the more annoying that sound is going to be to you. So later on in the exit ticket, I'm going to ask you guys some more questions about the Doppler effect, but they love to phrase this question very, very strange. So it'll be something like, well, how is the sound relative to the detector? Or they'll ask you about the relationship between wavelength and frequency, and 9 times out of 10, it's asking you about this phenomenon, which is the Doppler effect. This is also going to come back up when we talk a little bit, when we do the earth science one, we're not going to spend too much time talking about meteorology because they don't really ask you about the meteorology side of earth science, but this is the same thing that gives us a meteorology map. So like the Doppler radar is the same thing here. Now a couple other things, because I want to make sure we have time to practice the equation. There are 2 types of waves. So we just talked about electromagnetic, which do not need matter or any medium to transfer their energy. So everything that is light can just pass right on through. It does not have to carry anything else with it. There are 2 other types of waves that we want to talk about briefly, and they are called mechanical waves. So in order to be a mechanical wave, you need some type of medium or matter to transfer through. So this concept of mechanical waves is going to come back up again when we talk about earthquakes in seismology in the earth science section. Okay. So just to remind you, a medium can be anything, any substance through which a wave can travel. Oh, sorry, that's for my kids. So not just like something like water or the ground or, I don't know, a plasma. It can be air. So if it moves the air with it, then it is considered a mechanical wave. If it's just passing through the air undisturbed, then it's on the electromagnetic spectrum side. We're gonna show you, I'm gonna give you some examples of 2 waves just in case these diagrams pop up. And then, like I said, we're gonna focus on the calculation piece here, how to calculate frequencies and wavelength. So the first type of mechanical wave is called a transverse wave. This is like an ocean wave. So this is energy that causes the matter to go back and forth at right angles. So up and down, essentially. The traditional wave that you might see. For anybody who ends up teaching physics, slinkies will be your best friend when you teach this unit. It's a fun way to teach the kids the difference between the waves. So transverse waves are up and down, and then we'll talk about longitudinal in just a second, which is also called a compressional wave. In our transverse waves, there's a couple pieces of vocab that are going to be important to us here. So the crest is the highest point of the wave. The trough is the valley in between. So when we measure wavelength, we'll be looking from crest to crest or trough to trough. So the peak to peak or valley to valley is the wavelength of a transverse wave. I'm gonna hold for 2 seconds because I see some people writing, so I don't want to move too fast ahead.
Can you hear me?
Yes, ma'am.
Will we get these slides at the end?
I sent them out already. I sent them out around 5:45.
Okay. And
So
last night's too?
Yep, I will send those out too. I'm just editing them to take out like all the stuff that we didn't get to last night.
Okay.
And then it takes Zoom almost 24 hours to synthesize the video, so that's why I wasn't able to send the video last night, but it should be done today.
Okay, thank you.
So like I said, the wavelength is just a measure between crest to crest or trough to trough, so the peaks or the valleys. Just remember that it's not crest to trough, it's peak to peak or valley to valley to give you the wavelength of a wave, a transverse wave. And then amplitude is going to be the greatest value of the wave. So the highest you can go or the lowest you can go undisturbed will be its amplitude. Now, most often, the test is going to ask you to calculate the wavelength. So after we talked about a compressional wave, again, this is where we're going to focus. We'll do a formula triangle, practice some examples to get that problem down.
Can you give us an example of a amplitude wave?
Oh, amplitude is just a measurement. So if it asks you like, what is the amplitude of this wave? It means you're looking for the highest peak on a, does that make sense?
Yeah.
Yeah, so it's just if you had a baseline measurement through the highest peak that you would reach or the lowest of the low, that would be your amplitude. The other type of wave is the compressional or longitudinal wave. So transverse waves go up and down like an ocean wave. Compressional waves are like an accordion, so in and out. Okay. Anybody here into music or make music or pretend to be a DJ like me in my head? No, just me, okay. Well, if you're into music, then you have seen a lot of compressional waves because they look like this. Okay. Compressional waves are a little bit stranger to read, but where the lines are gathered close together, that is a compression. And then where the lines are spread apart is a refraction or a fraction. So just like in a transverse wave, where the space between crest to crest or trough to trough is the wavelength, in a compressional wave, the wavelength is measured from either compression to compression or refraction to refraction. Same thing. Now, no matter if we're looking at a compressional or a transverse wave, the way we calculate wavelength, frequency, and speed is all the same. I'm going to give us a formula triangle in just a second, but just so you know, so you're not looking at me crazy. In physics, wavelength, again, that space between, is signified by the symbol lambda. So frequency will be F, wavelength will be lambda in these equations, and speed will be C. So just like we talked about speed is distance over time, the wavelength formula, the velocity, which is speed of a wavelength, can be calculated by the frequency times the wavelength itself. So speed or velocity is frequency times length. So that means if you wanted to calculate the frequency of a wave, it would be the velocity divided by the length. And if you want to calculate the frequency, it'd be this is velocity divided by length. If you want to calculate the length, it's velocity over frequency. So same formula triangles that we did yesterday. If you weren't on the call with us, the way a formula triangle works is whatever variable you're trying to find, that's what's highlighted, and what's left over is what you manipulate. So if you're trying to find frequency, velocity is sitting on top of length, so you would divide the velocity by the wavelength. Okay. If they're on top and bottom, you divide. If they're next to each other, they multiply. So let's look at a couple examples, and then this is what we're going to practice for about 10 or 15 minutes tonight to make sure that we got the actual concept down here. So our first example problem is here. It says a wave has a frequency of 50 hertz and a wavelength of 10 meters. What is the speed? So to remind us, our formula, V or C can be your speed, and then we have frequency and wavelength represented by the lambda. It's asking me for speed, which means I'm trying to find the top part. So that means I'm going to say my velocity is equal to my frequency times my wavelength. So V is going to be equal to 50, which 50 hertz is my frequency, times the length of 10 meters. So my speed here is 500. Make sense? And then the unit here would just be, you could say meters per second, meter or hertz per second, hertz per meter here. Simple enough. We're gonna do 2 more. Does anybody need me to go through this one again? Wow, that cleared up quickly. Okay. Our next one says a wave has a frequency of 5 hertz and a wavelength of 25 meters per second. I mean, a wave speed of 25 meters per second. I should say speed, I'm sorry. What is the wavelength? So I'll go back and fix that. Again, looking at our triangle, velocity, frequency, wavelength. For this time, if we're trying to find wavelength, that means we're trying to find the lambda. So wavelength is going to be our velocity divided by the frequency. So in this case, my velocity or my speed is 25 meters per second divided by a frequency of 5. So my wavelength is just going to be 5 meters. Cool. Let's do one more together. Yes, thank you. And then we'll break into some smaller groups. This one says a wave has a wavelength of 10 meters and a speed of 340 meters per second. What is the frequency? So before I do this one on the screen, I want you guys to take 30 seconds to do it on your own before I set you off.
I don't remember the formula for the frequency.
Okay, I'll put it back up there. Velocity, frequency, wavelength. So if we're trying to find the F now, we're gonna do what over what?
Velocity.
Mm-hmm.
Velocity over, what's that, wavelength?
Yeah, that weird little lambda is the wavelength.
So 10 divided by 340.
Other way. So if we have frequency, our velocity is the speed right here.
Mm-hmm.
So that's going to be 340 divided by 10, which means the frequency would be what?
34.
34.
Yeah.
Yep. And then it's free. So we have 34 hertz really, which is the same thing as meters per second. On the Praxis website that we're absorbed by 10 grams of water as the temperature is increased from 30 to 50 degrees Celsius. This is a chemistry problem, technically. And in order to do this, you kind of need an equation. Now, remember, when you take the test, it's going to give you that list of common equations in the beginning. So it will give you the equation that you need for this one, and it's called the specific heat one, specific heat equation. So in order to calculate heat energy, if you ever see a temperature change, you have to remember Q equals MC delta T. So in Q equals MC delta T, M stands for mass, C stands for the specific heat of water, and delta T, like we said yesterday, delta means change, T for temperature. In that table, it will also tell you that the specific heat of water is 4.18 or 4.19 joules. So to calculate the Q, which Q stands for heat, you just multiply the specific heat times the mass times the change in temperature. Now remember, you won't have a calculator, so the chances are that they're going to give you numbers like 10, 4.18, and 20 to do the math on are relatively slim, because you would probably need a calculator to multiply that out. But if you ever did have a problem, you would plug in Q equals MC delta T, multiply those out, and the answer would be 838 joules for energy. So I gave you this one just in case somebody did, my last participant who had the middle school test said she did have a couple of equations, but the numbers were very friendly. So it was like 10, 4.19, and another 10. So they were very easy numbers to multiply, but she did say this equation came up. So if you ever need to calculate heat, heat is measured by joules and is represented by the letter Q. So again, we're going to use the formula Q equals MC delta T and multiply everything out to get our Q value. So the answer should be 838. On the document I'll send you, it's going to look similar to this. So it'll have the questions, it'll have what it's aligned to, the correct answer, and each of the questions will have an explanation of how to solve them if you ever need to go back. Second most missed question is this one. This one we kind of started talking about yesterday. So it says a body goes from point A to point B with a velocity of 4 kilometers per hour eastward and returns from point B to point A with a velocity of 60 kilometers per hour westward. What is the average velocity of the body during the entire journey? What were you guys thinking for this answer?
0.
Why 0?
The displacement is 0.
You are 100% correct. Because the displacement is 0, the velocity must also be 0. I think some people were thinking about speed because the formulas are so similar. So speed is distance over time, but in this case, because the displacement is 0, we have no velocity. So great catch. Great catch there. Questions on this one? I love the confidence that one. I was like, 0, I got it. You do. Proud of you.
Oh, that's good.
The next one. Metals conduct electricity well. Which of the following properties of metals accurately accounts for this observation? What are we thinking?
C.
Yes, did we went through this question already, didn't we?
Mm-hmm.
Yeah.
Okay.
A similar one.
I can't remember. Okay, I was like, I feel like we did talk about this question already. Just to review though, A, if it's talking about transferring, which bonds are transferring electrons? Anybody remember?
Ionic.
Ionic, and what type of compounds make up ionic bonds?
Metal and non-metal.
Metal and a non-metal.
Whoop, whoop. So for A, that is ionic. B is talking about sharing. So sharing would be what?
Covalent.
Covalent. And covalent bonds are formed between what?
Non-metal, non-metal.
Non-metals.
You guys are awesome. Why am I on this call? And then D would be knocked out because again, it's talking about covalent. So great job. Again, the answer here is C. This one is a balancing equations problem. Okay. So we didn't get a chance to go over balancing on a call. So what I'm going to do is talk it out and then I'm going to draw it out on my board. But we already know that I don't know how to talk and draw at the same time. So I'm going to talk this out and then I'll show you guys how to solve it quickly. So in chemistry, the arrow in the middle means yield. So everything to the left of the arrow is considered to be our reactant. Everything to the right is our product. I always tell my kids to think about this like baking a cake. Everything you put into the cake yields the cake itself. In chemistry, we operate by the law of conservation of mass or matter. They're the same thing, or energy, it's all the same. What it means is that mass and matter can be neither created nor destroyed, it can only be transformed. So when we have chemical equations like this, and these little numbers, I'm sorry, should be subscript, they should be down below. You have to add coefficients in front to show that however many lithium molecules you started with are still present on the other side. So balancing is really just like a check and balance system. You don't really have to kind of do any math. It's very simple multiplication. But one thing that's important to note is that when you add a coefficient, it's going to multiply to the entire molecule. A subscript only applies to the molecule right before it. So an Li3N, that means I have 3 lithiums and 1 nitrogen. If I were to put a 2 in front of the Li3N, then I would have 6 lithiums and 2 nitrogens. It would distribute and multiply to everybody. So when we balance this equation, we're just going to count what we have and try to add coefficients to make sure everything is the same. Let me erase my board. We always tell our kids just to make like a check and balance and tally system when they're balancing. So first thing I'm gonna do is just rewrite that equation on my board so I have it. So all I did on my board was rewrite the equation, and I put an arrow, I put a line down the middle where my arrow is to separate my reactant from my product. Before I start balancing anything, I'm just gonna write down what I have so that I can easily keep track of all my elements. So on the reactant side, I listed out, I have lithium, nitrogen, hydrogen, and oxygen, like that. I'm gonna do it on the other side, and I'm gonna keep it in the same order just because it'll be easier for me to check my numbers as I go through the problem. On the reactant side, how many lithiums do I have?
3.
3.
And how many nitrogens?
1.
How many hydrogens?
2.
2.
And how many oxygens?
1.
1.
Now, on the other side of my arrow, how many lithiums do I have?
1.
How many nitrogen?
1.
1. Be careful with this one. How many hydrogens do I have?
2. 3. No, 4. 4. 4.
4. 3 plus the 1 by itself, so there's actually 4. And how many oxygens?
1.
1.
1.
So as of right now, the only things that are balanced are the nitrogens and the oxygens. So to balance this out, one rule for balancing that will always help you, if you have an element that's split up, like we have hydrogen in 2 different places on the right side, never start with the one that's split. Always start with the one that's already together. So when I start to balance, I'm gonna start with the lithium. I have 3 on the left side, 1 on the right. So what coefficient can I put in front of that lithium to make it a 3?
3.
Yeah.
I had to squeeze it in there because this board is kind of small. So lithium's good, nitrogen's good. I still have that hydrogen problem. How do I make the hydrogen on the left side of 4?
2.
Now, when I add that 2 in front, what does that also change?
Oxygen.
So I now have, how many oxygens do I have?
2 on the left, 1 on
2.
the right.
So now we have one more step. We balanced the hydrogen, but we threw the oxygen out of balance. So I've got 2 oxygens on the left, 1 oxygen on the right. How do I fix that?
2.
Now, if you notice on the board, it says that my answer should be 3, right? We put a 2 there, and that fixes the oxygen, but when I put that 2 there, what did it actually do to my hydrogen?
Made it a 4.
It made it 2 plus 3, which is
5.
made it 5. When you end up with an odd number, you have to do a little bit more finagling because you want everything to be even. There's no way to make 5 hydrogens. If you make 5 hydrogens on the other side, you keep messing everything up. So we could keep doing this, but it's already 7:51. If you've written that example down, you'll see that if you go fix the hydrogen on the other side and make it a 5 in front, you'll have no choice but to change the other oxygen to a 3. It'll take a little bit of finagling, but what I always tell my kids to do is to make every odd and even. So if you ended up with 2 plus 3 is 5, go back to the one that you just changed and fix it so that the total is an even number. So I would tell them to change it to a 3 because 3 plus 3 is 6, and the whole thing will balance out a lot easier.
Okay.
Balancing takes practice, especially for people who are not too familiar in the chemistry realm. So when I send out the stuff tonight, the answers and everything, I will also send some extra help for balancing because this is where it tends to get a lot of people on the chemistry side. Questions on this one, guys, that I can answer immediately?